After studying this module, you shall be able to know about metalloboranes and metallocarboranes, structure and bonding in metalloboranes and metallocarboranes, methods of synthesis of metalloboranes and metallocarboranes. Borane cages possessing one or more metal atoms but no carbon atoms in the skeletal framework are known as metalloboranes. These compounds were mainly formed by the reaction between boron or carborane hydrides and neutral metal atoms, or between boron hydride anions and cationic metal ions. The structure of these compounds varies from 4 and 5 vertex species to multi-cage macropolyhedral systems. Initially working with carboranes, the icosahedral 1,2-C2B10 H12 carborane cage was found to be reduced to nido C2B9 H11 2-, known as the dicarbolide ion, by the removal of one BH2 plus vertex. This is shown in figure. It is evident from the above shown reaction that the removal of a BH vertex converts the neutral closer structure into an open nido carborane with 2 negative charges. This leads to the observation that the C2B3 open phase in this species was similar to C5H5- ion and offers 3 pairs of pi donor sides. Therefore, the transition metal ions should form neta-5 coordinated sandwich complexes analogous to metallocenes. The anionic structure left behind after the removal of the BH2 plus unit act as an efficient anion having the ability to react with a variety of transition metal complexes. For example, on reaction of the nido C2B9 H11 2- carborane anion with Fe2 plus ion leads to the preparation of a diamagnetic ferrocene analog complex 1. This sandwich complex showed similar properties as ferrocene, such as redox properties. NMR studies reveal that the metal unpaired electrons were not delocalized onto the carborane cage completely. This carbonyl ligand has been combined with a number of transition metals to form metal complex and stabilize the later transition metals in higher oxidation states. Similarly, this methodology was applied to boranes, such as the reaction between B5H9 and FeCO5 resulted in the formation of complex 2 with in situ replacement of one of the apical BH unit with FeCO3 fragment. This is shown in figure. The stabilization of higher oxidation states in the sandwich complexes can be ascribed to the greater electronegativity of the carbonyl ligands. These sandwich complexes are of 2 types, where the symmetrical sandwich complexes are formed by early to middle transition metal ions, and the slipped sandwich complexes are generally formed by the later transition metals. This is depicted in figure, and also there are some common examples of metallocarboranes. Now, we shall have a look at the synthesis of the metallocarborane. Because of the higher reactivity of borane substrates with metal reagents, particularly the smaller ones, the attack of the first metal atom frequently occurs at more than one site. Hence, the incorporation of the first metal promotes further reaction to form higher order structures, which often result in complex mixture of number of metalloborane species. The most common method to synthesize the metallocarborane is by the direct reaction of a carbonyl anion and metal cation, which has been described. Apart from this, there are 3 other synthetic methods to achieve metallocarboranes. The first method is called the degradation method, which can be illustrated by the cobalt 12-C2B9H11 twice 2 negative ion. The treatment of this ion with 30% NaOH and excess of CoCl2 for several hours resulted in complex 3. The structure of complex 3 is shown as: the complex 3 is a double sandwich complex with 2 cobalt ions and 3 carbonyl ligands, where the central ligand is formed by losing 2 BH units to act as a bidentate ligand, while the other 2 axial ligands are formed by the usual loss of one of the BH units. The polyhedral expansion method involves the reduction of the carborane with sodium into an activated form, followed by reaction with the metal ion or metal and cyclopentadiene ions. The resulting product is found to have one more vertex than the parent carborane. For example, the reaction between 1,7-carborane, that is the 1,7B6C2H8, which is a 10-vertex polyhedron, and cobalt ions leads to expansion of the parent carborane twice to insert 2 metal atoms to give the complex 4. The structure of complex 4 is the direct insertion method display broad applications in the field of metalloborane synthesis, particularly with smaller carboranes. For example, the reaction between 1,5C2B3H5 and FeCO5, or the complex eta5C5H5 cobalt carbonyl twice at high temperatures of over 200 degrees centigrade resulted in the mono and dimetallocarboranes as shown in the figure. Metalloborane synthesis by metal insertion into a carborane anion at room temperature is often more controllable and provides a single isomer. However, other synthetic routes such as metal insertion into a neutral carborane at high temperature results in the mixture of isomers, and such approach are not in practice these days. Commonly used methods are shown: C2B9H11 2- treated with nickel 2+ with THF and air leads to NiC2B9H11 twice. Another example, C2B9H11 2- with the ferrous ion in the presence of C5H5- THF as a solvent and in the presence of air gives to CpFe C2B9H11. Again, another example is Et2 C2B4H4 2- plus cobalt 2+ ion in the presence of cyclopentadiene anion and THF and air gives rise to CpCOEt2 C2B4H4 complex. Now, we shall have a look at the bonding in the metalloboranes and the metallocarboranes. In metal containing clusters such as metalloboranes, it can be assumed that each metal atom occupying a vertex in the cage utilizes 3 orbitals for bonding with the nearby bonded atoms in the cluster framework. The main group metals have 4 valence orbitals, hence one of the orbitals is free to bond with the external atom or group such as hydrogen, alkyl and halogen, etc. However, transition metal complexes have 9 valence orbitals. Therefore, apart from 3 cage electrons, offer 6 extra orbitals to bond to the external groups and to store non-bonding electrons. Taking example of the metalloboranes containing metal cyclopentadienyl based metal vortexes in a COCP fragment which has 14 electrons, the 3 orbitals are engaged in bonding with CP ring. The other 3 orbitals are involved in bonding with the carborane framework and 3 orbitals remain available for electron storage. Counting electrons in such complexes, the bonding arrangement of cobalt to CP ring requires 6 electrons. 6 electrons are non-bonding and 2 electrons are available for cage bonding, and hence COCP fragment is isolobal with the BH unit in a borane framework. Applying the similar method, the commonly seen FeCO3 fragment is also a 2-electron donor and the CpNi offers 3 electrons, which is analogous to CH. Therefore, FeCO3 and COCp fragments replace BH units and CpNi replaces BH units in the carborane frameworks. Now, we shall summarize what we have learnt in this module. Borane cages possessing one or more metal atoms but no carbon atoms in the skeletal framework are known as metalloboranes, where these structure varies from 4 and 5 vertex species to multi-cage macropolyhedral systems. Metalloboranes or metallocarboranes can either lose a BH2 plus unit or a CH plus unit to generate anion carborane, which can act as a ligand to make bonds with various metal ions. For example, on reaction of the nido C2B9H11 2- carborane anion with Fe2 plus ion leads to the preparation of a diamagnetic ferrocene sandwich complex. The sandwich complexes of carboranes are of two types, where the symmetrical sandwich complexes are formed by early to middle transition metal ions and the slipped sandwich complexes are formed by the later transition metals. The most common method to synthesize the metallocarboranes is by the direct reaction of a carbonyl anion and metal cation. Other methods are degradation method, polyhedral expansion method and direct insertion methods. In carborane and metal cyclopentadienyl complexes, the bonding arrangement of cobalt to Cp ring requires 6 electrons. 6 electrons are non-bonding and 2 electrons are available for cage bonding, and hence COCp fragment is isolobal with the BH unit in the borane framework.